for giving this opportunity to present my research. This is the title of my presentation. Learning-based revision enhancement in SAR imaging for automotive laser sensors. So let me start my presentation. The table of contents for this presentation is as follows. First, I will give an introduction, and then I will tell you about laser signal measurement in relation to signal loader of the laser system and the measurement environment. Next, I will talk about SAR image formation method using acquired data and tell you about the results. Then I will discuss the proposed resolution enhancement method and close with a conclusion. So this is an introduction. Synthetic observer refers to laser systems that forms an image by synthesizing signals reflected from ground or target. Typically, SAR systems use aircraft and satellites as platforms for surveillance and reconnaissance purposes, and measurements are made as shown in the figure on the left. However, research on automotive SAR for recognizing the surrounding environment of intelligent vehicle has recently been increasing, and an example can be seen in the figure on the right. So high-resolution SAR image formation is essential for environmental recognition and targeting. However, this requires regular data acquisition at high sampling frequency. Data required by high sampling frequency increases the size of data, and data loss may occur, or non-idle data may be corrected for various reasons, as shown in the figure on the left. Therefore, this study proposes a method to translate low-resolution SAR images formed using limited sample data into high-resolution SAR images. The figure on the right is the flow chart of this study. Data is collected through experiments, and high-resolution SAR images and low-resolution SAR images are formed based on the data. Then, learning is performed using data from both domains, and performance is evaluated on the output of the learning network. Next is the signal model of FMCW radar using the measurements. As shown in the block diagram on the right, a radar consists of various elements, including a transmitter and receiver. The waveform generator generates pulses during a certain period, and transmission signal to the nth pulse is as follows. The signals reflected from K targets are as follows, where the distance and speed of the targets can be estimated through time delay and Doppler shift. Then the signal passing through the frequency mixer and low-pass filter is expressed as P sub n of t. And the signal sample through the analog to digital converter is expressed as large P sub n. Finally, the raw data acquired through the radar sensor is equivalent to large R. Measurement environment. In the measurement, TI's AWR642 boost was used, and the parameters set in the radar are shown in the table. The radar was set to a center frequency of 77 GHz and bandwidth of approximately 3 GHz, with the remaining parameters shown in the table. The experimental environment is as shown on the right, and the radar was attached to a movable platform and moved linearly at an average speed of 1 millisecond. Additionally, measurements were conducted in an environment where 6 vehicles were deployed. So data acquired through measurements from the SAR image through the range Doppler algorithm. The RDA process forms a SAR image through a preprocessing, lens compression, azimuth direction FFT, and azimuth compression as shown on the left. The raw data appears as follows. And in the preprocessing step, the average of each lens axis is subtracted to remove the direct current component. Afterwards, through the fast Fourier transform on the lens axis, the lens compression result appears as shown in the figure on the right. Similarly, FFT is applied in the azimuth direction on the lens compressed data, and the massive filter is used for azimuth compression. The formula on the left represents the migration factor, and the formula on the right represents a massive filter using it. In other words, a massive filter using a migration factor was used, and the result of azimuth compression performed through this is shown in the figure on the right. Therefore, as in the experimental scenario, 6 speakers are represented in the SAR images. The SAR image excluding lens cells beyond 10 meters appears in the next slide. These are results of SAR image formation. The SAR image formed using all of the sample data is shown on the left, and SAR image formed using only 25% of the sample data is shown on the right. Two former low-resolution SAR images that using only one pulse out of 4 is used, as shown in this figure. Therefore, this study proposes a method to enhance the resolution of the low-resolution SAR images on the right. This is a proposed method for resolution enhancement. Unsupervised image-to-image translation is a branch of the image-to-image translation problem, which is the method of reconstructing given input data into in the desired format. As shown in the figure on the left, there is an example of translating a daytime image into a nighttime image. And the unit network is used for data restoration and polarization. Additionally, input data sets such as training data set and test data set are required for unit network running. So, the generative process of the input data set is as shown in the figure on the right. Input data sets for each domain are generated by sliding a window with a length of 8.5 meters in the azimuth direction at 1% interval. Among the generated data, 95% is used as training data, and remaining 5% is used as test data for verification. So this is a structure of the proposed unique GAN. The proposed network consists of one generator and two discriminators. Among them, the generator takes data from two domains as input and aims to run the joint distribution for the two domains. As shown on the left, the generator consists of encoder parts, shared parts, and coder parts. The encoder is responsible for downsampling the input data and extracting features for each domain. In the shared part, data from different domains are merged through a computation layer to run the joint distribution of the data. Afterwards, the decoder upsamples the processed data and returns output corresponding to the domain type. The figure on the right represents the structure of each discriminator. This is a patchy GAN structure using general GANs and determines the authenticity of the data based on downsampled data by the patchy size instead of entire data. In this discriminator, the size of generated data is reduced by 4 times, and authenticity is determined using the reduced data. Next are the results translated via the proposed network. The performance evaluation is performed based on test dataset not used in the training process. The figure presented in the table shows two images from the test dataset as examples. In order from the left on the table, these are high-resolution SAR images, low-resolution SAR images, and images translated through the proposed method. Comparing the second and third columns of the table shows that the image quality has improved. For a quantitative evaluation of the proposed method, image quality metric PSNR and SSIM are calculated. The values shown on the right are the average values of PSNR and SSIM for the test datasets. Compared to existing low-resolution SAR images, the SAR images of the proposed method improved PSNR by 2.75% and SSIM by 4.43%. This is the conclusion of this presentation. To summarize this study, it is as follows. Data is acquired using automotive radar, and the RDA method is applied to form a SAR image. According to the sample data, high-resolution SAR images and low-resolution SAR images are formed. Then, unique GAN learning is performed using data from each domain. After learning was completed, the SAR images translated through the proposed method improved PSNR by 2.75% and SSIM by 4.43% compared to existing low-resolution SAR images. So this is end of my presentation. Thank you for listening.